In this video lecture, I will introduce the surface area problem, and we will solve the surface area problem for solids of revolutions. And first, let's start with defining what the problem is. To solve the surface area problem means we have a solid three-dimensional object, and as a three-dimensional object, it has volume and surface area. So let's just draw some three-dimensional object here. It's really hard to draw a generic object, but whatever that object is, it has the inner part of itself that can have a volume, and the surface, which is kind of the outline of the object, and the surface has the area. So in general, finding the surface area of any three-dimensional solid is a hard problem. We're not going to attempt to solve that problem. However, we are going to attempt, and we will solve the following surface area problem. So if we have a function f of x defined on some interval from a to b, and it is continuous and differentiable, and if we create if we take a piece of this function and if we rotate it around the x-axis, then by doing so we'll create something that is called the solid of revolution. So if we look at it sideways, it's going to look like a vase. But in this particular case, like in this problem, we are going to consider this solid of revolution. It's a solid that is obtained by rotating a piece of a function around one of the axes. Unlike some generic solid, solids of revolutions have some nice properties, and we clearly have now defined this surface area. So visually, we know what we're looking for. Now, this part of the solid is called the lead. So it has two leads, and we're not going to include the leads in the surface area because they're just two circles, and we're not really concerned with finding that area. It's very easy. So to find the surface area means to find this area that I just drew over here for some solid of revolution. And again, it's still a hard problem because f of x could be any curve, and let's check for which curves we already know how to find the surface area. So let's call this section prerequisites, and let's investigate what we already know about the surface area. So for example, if we take a piece of a horizontal line and rotate it around the x-axis, we're going to obtain a shape that is well known as a cylinder. And every cylinder will have the radius of its circular base, and it has the height, and it is pretty clear what the surface area is in terms of geometry. But in terms of what the value of it is, here's what we're going to do. We're going to take this cylinder and we're going to cut it right here. And when you cut it, you will be able to open it up, And if you cut it and open it up, you will get a flat sheet of the surface. And let's look at the dimensions of it. So what used to be the circumference of a base is now a side of a rectangle, and what used to be the height is now another side of this rectangle. And using the circumference of a circle formula, we conclude that this is 2 pi r, this is h, and the surface area now can be found by simply using this formula, base times height, so 2 pi r h. So we definitely know how to find the surface area of a cylinder. All right, what else do we know? Well, the next shape that we're going to consider is a cone, and cone can be obtained by taking a line that passes through the origin and rotating it around the x-axis. So this is the axis of revolution, and cones are also defined by the radius of its base, and usually cones are also defined by the height of a cone, but the formula in terms of the height is not as nice as the formula in terms of the length of the side of the cone, so which we will label as L. And again, we clearly identify what a surface area of a cone is geometrically. So now to find it, what we're going to do, we're going to cut this cone open. And when you cut the cone open along one of its sides, you'll obtain a piece of a well, it's called a sector. It's going to be a sector of some circle. And what do we know about this sector? We know that what used to be L is now the radius, and what used to be the circumference of the base is now a piece of this arc. And for everything we do have formulas, as we are familiar with this geometric object. So if we introduce this angle theta, then the following relations are true, right? So this is going to be L, and if that's L, that this will be theta times L if theta is in radians, and on the other hand, it's going to be 2 pi r because it came from the from that cone. And now we can do simple math here to find this surface area. We just use this formula from trigonometry, 1/2 theta L squared, and then we can rewrite it like this. I'm just manipulating to end up with something nice, and theta L is exactly the same as 2 pi r, and L, if we just leave it alone, then we get this formula, pi r L. So we know how to find the surface area of a cone. All right, so as long as we can make our solid of revolution to look like a cone, then we're all set. Unfortunately, that's not going to happen, and we need to also consider a third shape, which we would consider basic shape, and that basic shape is obtained by taking a piece of a line, so it doesn't have to go through the origin, and rotating it around some axis, and in doing so we're going to obtain what's known as frustum. And we're going to define a frustum in a similar way we defined a cone. So we're going to have the radius of the one base, then the radius of the other base, and we're going to define the frustum also by the length of this line segment connecting the two bases. And the question is, what's the surface area? So geometrically, it is pretty clear what it looks like. Now let's find numerically the area. And to do this, we're going to use a simple principle that says, well, first of all, we're going to complete this picture. We're actually going to extend this line. I'll use different color here. We're going to extend this line all the way until the axis of rotation. And then by doing that, we complete this picture, and now it looks like a cone. And we actually have two cones here. So the surface area that we're interested in finding can be found by taking the surface area of a larger cone and subtracting the surface area of a smaller cone, which forms the tip of that larger cone. And if we do that, then what's left is going to be the area of a frustum. And the only thing we need to do now is figure out the areas, the surface areas of those cones, and that's actually pretty easy because we have a formula for the surface area of a cone right here. In our case, let's introduce another variable. Let's call this S. So this piece of a line segment, and then the surface area of a bigger cone will be pi r, and remember it's that L, but in this case the L, it's the sum of these two lengths, so it's going to be S plus L, and the surface area of a smaller cone is simply, I should add 2 over there, it's going to be pi r1 times S. So the only problem is that we don't know what S is. It was created geometrically. We don't know exactly what S is. So to find S, we're going to consider the following projection, not the projection, cross-section, or not even the entire cross-section, but a part of the cross-section. And this is R2, this is R1, this is L, this is S, and here's what we can learn by looking at this diagram. We have two similar triangles, so therefore the proportion is preserved. So S over R1, it's the same as S plus L over R2, which means, so actually let me write this over here. And what this means is that we can now algebraically solve for S. So to do that, we're going to multiply both sides by R1, R2. We're going to do some algebra here, and finally we obtain the following expression, and therefore we can now plug it in into the ongoing formula. So here we have pi r2 R1L over R2 minus R1 plus L minus pi R1L over R2 minus R1, and now we just need to simplify it. And we're probably going to have this 1 over R2 minus R1 over here. We're going to take out pi as well. And now let's deal with everything. So what's left of the first part of the expression is R2 R1L plus L R2 minus L R1, and what's left of the second expression is minus R1 squared L so it looks like we can do some simplification here. We can take out L, so we have pi L over R2 minus R1, and here we have, if I combine this term and factor out R1, we get R2 minus R1, and then we combine these two, we get something's missing here. Hold on. We should have R2 here somewhere. R2, I think I forgot to multiply this by 2, so we have this, we have another R2 over here. After we distribute this R2 over here and over here, we get an extra R2 over there. So it's going to be like this, R2. Actually, then it becomes even easier. So this cancels this, we don't have to group anything. And then we just have the difference of squares. And that can be simplified into this. And now, for the sake of notation, I'm going to introduce a new variable using which the formula for the surface area of a frustum looks like this. It's going to be 2 pi r bar L, where r bar, it's the average of the two bases. So we finally got the formula for the surface area of a frustum. All right, so now, as long as we can break the surface area of some generic solid of revolution into frustum, we're good, and that is actually possible. So we're going to set up the surface area of a solid of revolution problem like this. We're going to have a piece of function f of x, and we're going to rotate it around the x-axis, and all of that is on some interval from a to b, and we're going to rotate it around the x-axis, as I said, and in doing so we're going to create this solid of revolution. And again, the surface area visually is pretty clear. So this is the surface area that we are looking for. And the first thing we're going to do is we're going to create a partition of the interval from a to b. So we're going to break it up into n subintervals. And as we have seen before, that will create this collection of points on the curve, which is some f of x, right? So let me write this over here. So this is some function f of x. And we're going to label these points P0, P1, P2, and so on. Pn, Pn minus 1, Pn minus 2. And we're going to be focusing on some ith interval, which generates the points p with index I minus 1 and p with index I. And instead of looking at the surface area of the entire solid, we're actually going to consider these line segments. And for each of these line segments, when you rotate it, so again, if we take this line segment and rotate it, we are going to get a frustum. So the total surface area can be approximated with the sum of this little surface areas of those frustums, right? So again, here's the frustum, and here's its area, right? So it goes all the way around like this. All right, and let's focus on the ith frustum. So let's find the surface area of ith frustum, and to know the surface area, we have to know the radius of the top, radius of the bottom, and the length of the side. And in our case, the one of the radii is f of x I, and the other radii is f of x I minus 1. So the surface area of the ith frustum is 2 pi r bar times L I, and the Ri bar, it's the average of the two bases of the radii. So in this case, it will be this, which is f of x I minus 1 plus f of x I over 2, and L I is the length of this line segment that connects the 2 points, Pi minus 1 and Pi. To find the arc length of that line segment, we're going to pick a point that satisfies the mean value theorem on that interval, xi star, and we're going to now use that xi star to compute this this arc length. it's going to be the square root of 1 plus f prime xi star squared delta x. And we're also going to do the following observation. As delta x goes to 0, the xi and xi minus 1 will close on that interval, and both of them will approach to f of xi star, meaning that the r bar on that interval can be approximated with the following expression. And finally, we now can put it all together. So the surface area of the ith frustum can be found with this formula: 2 pi f of xi star times the li, which is the square root of 1 plus f prime xi star squared delta x. And we are near the end of solving this problem, because now we just have to put it all together one more time. And we have the surface area of ith frustum is, according to our formula, it's 2 pi f xi star square root 1 plus f prime xi star squared delta x. Therefore, the surface area of n frustums is, so now we're gonna add them all together. And now the surface area of infinitely many frustums will be this expression, but with the limit as n goes to infinity. But we know that the surface area as n goes to infinity of n frustums, if exist, must be equal to the surface area of that solid of revolution. However, on the one hand, that's the case. On the other hand, we're looking at this limit, and we totally recognize this Riemann sum pattern, and we therefore conclude that this limit must be equal to the integral from a to b of 2 pi f of x 1 plus f prime x squared dx. And let me make this a little smaller. And this is going to be our surface area formula for the solids of revolution. One of them. So, to summarize, did we solve the problem? Yes, we did. The surface area can be found by computing this integral. And just like before, it's not about just throwing f into this integral. We kind of have to practice this as a process. And let's do an example. Let's find the surface area of a solid obtained by rotating a piece of this function on the interval from 1 to 4 around the x-axis. So the picture would look something like this. We have a piece of a radical function, and we're rotating it around the x-axis. So it looks like kind of like a bucket sideways. And we're going to do it in steps. First thing we're going to do is we're going to find the derivative of the function, which is 1 over 2 radical x. Then we're going to plug in everything into that radicand and try to simplify. So f of x is square root of x. 1 plus f prime of x squared is this. And we don't want to throw everything in the integral and then spend a lot of time trying to simplify it. We want to simplify it first and then put it inside of the integral. So to simplify this, we get because x is positive, we can combine these two radicals and we end up with something like this. It's going to be x plus 1/4, and now we can find the surface area by putting it all together. We have integral from 1 to 4 of square root of x plus 1/4. And I forgot 2 pi. Usually 2 pi is written outside of the integral because it's just a constant. So let's do that, and then let's find this integral by using the fundamental theorem of calculus. And antiderivative of that function is 2x plus 1/4 over 3 to the power 3/2, and now we have to evaluate it between 1 and 4. So again, two distinct parts: setting up and solving the integral. You can solve the integral right, but if it's the wrong integral, then the problem is solved incorrectly. You can also set up the integral right, but then make a mistake finding it, and that will also lead to an incorrect answer. So to finish this, let's just plug in 4. So we have 17/4 to the power 3/2 minus 5/4 to the power 3/2. So this is the exact answer. If we want an approximation, we would just throw this in a calculator. Now, just like with the arc length, we can define a surface of revolution as a rotation around the y-axis. So if y is equal to f of x, we can rotate it around the x-axis, and in this case we have this formula. And And it's not hard to imagine that if we have defined a function like this, as x being the function of y, and then if we rotate it around the y-axis, then again, it's not hard to imagine that the formula for the surface area would simply be 2 pi integral from c to d, whatever c and d are. And then instead of f of x, we'll use g of y, and instead of dx, we'll use dy. And let's do an example. Let's take the same piece from the previous problem. But this time, let's rotate it around the y-axis. So what's going to happen? Now we have to set it up differently. We have piece from 1 to 4, so it looks something like this. Now we're rotating it around the y-axis, so it's going to go around like this. And we do want to use the formula that we just introduced, right? So we want to, we kind of don't have any other formulas, right? So we want to use this formula. The problem is we don't know what c and d, we don't know what g of y are, right? So that should be our first step, figuring out all these ingredients. And what's g of y? So if y is equal to square root of x, then in the first quadrant we can write it as x equals y squared, and therefore g of y is y squared. So we figured that out. Now, how do we figure out c and d? Well, c and d, it's the limits of integration on the y-axis, so c will be the limit that corresponds to x equals 1, and d will be the limit that corresponds to x equals 4. So to find these limits, we simply have to plug in those values into the function. So my c and d are 1 and 2. And once we figure that out, now we're going to start this process. So we're going to find the derivative of g first. Well, first we're going to clearly identify g. Then we're going to find its derivative. And then we're going to try and simplify this expression. So we have g of y times 1 plus g prime of y squared, and that's going to be y squared 1 plus 2y squared. And honestly, I don't see how to simplify it to make it easy to integrate. So let's set up the integral. We're going to have an integral from 1 to 2, and it's going to be 2 pi y squared 1 plus 4y squared. Now, this is not the type of integral I can do off the top of my head, so if it was one of the easy ones, I would, but in this case, I'm just going to put it in Wolfram alpha. So we're going to type integral from 1 to 2 and we integrate with respect to y, and we're going to type here 2 pi times y squared times square root of 1 plus 4y squared, and press enter, and the answer is approximately it's 49,416, and whatever the units are squared, because it's the surface area. All right, now in conclusion, we're going to well, first summarize what we've learned, and we're going to try to find a pattern in those two formulas that we just created, similar to the one that we have discovered when analyzing the arc length formula. So if we have something like this, so if we have a piece of a one-to-one function that can be, I guess let's start with listing the formulas, right? So if we have some function f of x, like let's say y equals f of x, and then if we rotate it around the x-axis, we get the following formula. We get 2 pi integral from a to b f of x 1 plus f prime x dx. And if we rotate it around the y-axis, then we actually have to redefine it, right? So we would have to look at this function from a different angle, and we would define this function as x equals g of y. And if that was possible, then the answer will be this. So these are the two formulas that we have. However, let's take a look at it at the micro level, what's going on here. So if we look at the piece of a one-to-one function, it's going to look like a little line segment like that. And if we draw the x and y axis here, so if we rotate this function around the x-axis, we're going to end up with something like this, right? So it's going to be a frustum this way. And if we rotate it around the y-axis, we're going to end up with a frustum like this. And let's notice something that when previously we referred to, so this is my dx here, this is my dy here. Previously we referred to something like this as ds. And if we try to do that again here, what would we notice is that the formula actually can be written in a simpler terms. We can replace that whole radical dx thing with simply ds. And the same will work on the right as well. We can replace that whole radical dy thing also with ds. Now, what is the common here between f of x and g of y in these two formulas? Well, f of x, it's the radius of rotation around the x-axis, and g of y is actually the radius of rotation around the y-axis. So we have this one universal formula that kind of combines everything that we know. So the surface area can be remembered as 2 pi times the integral of r, the radius of rotation, ds. And of course, the domain of integration will vary depending on the setup. So we're just going to put d over there. And in this formula, we understand that ds is this. And r is the radius of rotation. So this one, just by remembering this one formula, you can actually remember all formulas for computing the surface area. And not only this, it adds two more formulas to the list that we would have to remember. But let me show you what I mean by that. So it makes us more flexible in terms of how we can set up a problem depending on what's given. So when you have a problem like this, you have to look at, so let me draw this giant table. We're going to be looking at the, first of all, what's important is whether you rotate around the x-axis or around the y-axis. And the other thing that's important is whether your function is given to you as a function of x or a function of y. And depending on this circumstances, you will interpret this single formula in 4 different ways. So here you would set up like this. So this is your classic formula. Well, now it's classic. Now that we have seen it for 30 minutes, it became instant classic. And this is your other instant classic, right? So when the problem is given to you like this, you will not hesitate to set it up this way. However, we can also mix and match in here. So if you want to rotate around the y-axis, but your function is given to you as f of x, you can interpret radius of rotation to be simply x. And it will work. And similarly here, if your function is given to you as g of y, you can interpret the radius of rotation simply as y and set it up your problem like this. Isn't it great? So just by remembering this single formula, you are very flexible in terms of your ability to set up and solve problems. So let's go back and look at this problem again. But this time we're going to approach it with our knowledge and which case is it? So we're given, so let me remove all of this. Which of the 4 cases does what's given represents? So we're going to be using this formula, 2 pi r ds, and let's remove all of this. So this is what we have given, right? So we have a function from 1 to 4 rotated around the y-axis, and we're given a function like this, but we're rotating it around the y-axis. So we can actually find that surface area by setting up this integral. And in this case, we don't have to do anything then, right? So we just set it up. So it's going to be the integral from 1 to 4 to pi. R in this case is x, and ds is 1 plus f prime x squared dx. And the first step is we're going to find the derivative. And we're going to now simplify this expression. And I can bring the x inside because it's positive. And now we have the integral. We have actually, it doesn't come inside easily like this, right? So it comes in as a square. Let's set up an integral. So here we still have a and b, but here we're going to plug in as 1 and 4, and we still have 2 pi, and it's going to be this. Now it's a simple integral, and we actually even can do it by hand, but just to save time, and to do it by hand, so you would just complete the square inside, do substitution, and then it's going to be one of those nice, it could be like arc hyperbolic sine or something. But to save time, let's just use Wolfram alpha, and we're going to integrate from 1 to 4 to pi, and we just have a square root of x squared plus x over 4, and we're integrating with respect to x. And of course we would like this to be the same answer. Yes, it is hyperbolic sine of some sort, and the answer is, just like before, it is 49.416, which is exactly the same answer as we got earlier using different approach. So the main takeaway from this lesson is this formula. This is the main formula, and this formula can be interpreted in 4 different ways depending on what's originally given to you, which is great. So you can easily also see that the problems that were somewhat easy to solve or very special in terms of setting it up for arc length are also going to be special in terms of setting it up for the surface area. So yeah, we solved the surface area problem, not for all solids, but definitely for solids of revolution.